Hi everyone, welcome to MedGoto. In this video, we're going to be talking about hypoxia. By definition, hypoxia is inadequate tissue oxygenation. And we can also have extreme form of hypoxia, which is what we call anoxia. And anoxia is complete lack of tissue oxygenation. And before we go into the causes of hypoxia, let's look at how we can get oxygen from the atmosphere, right, to the tissue, right? So from point A to D, right? So starting from the atmosphere, like we mentioned in the previous lecture, oxygen moves based on pressure gradients. They move from high pressure to low pressure, right? So from the atmosphere, which is our P atmosphere, so from there, it's going to go into the airway, right? Which is going to be our PiO2, partial pressure of oxygen in the inspire gas. And then from there, it's going to go to the alveolar. And in the alveolar, to calculate the oxygen, partial pressure of oxygen in the alveolar, that's going to be our alveolar gas equation, the P capital AO2. And then this partial pressure of oxygen is going to determine the oxygen that diffuse through the alveolar wall and the capillary into the capillary, right? And then once the oxygen diffuses through in exchange for carbon dioxide, the oxygen is going to dissolve in the plasma. So the oxygen dissolves in the plasma. And the oxygen that dissolves in the plasma is what we call PaO2, right? The partial pressure of oxygen in the plasma, right? And this oxygen that dissolves in the plasma, right, is going to go from there, right, and bind to the, that pressure is going to determine the oxygen that will bind to the hemoglobin, right? So here we're going to have our hemoglobin. And of course, so P capital AO2 to P small AO2, and from there to hemoglobin, we're going to be our oxygen saturation. So it's from hemoglobin. And of course, from there, the blood is going to flow into the, from the pulmonary vein, it's going to go into the left atrium and from there to the left ventricle. And of course, we're going to pump the blood from the left ventricle into different parts of the body. And if you want to see how our pump is doing, right, in terms of getting the blood out into the other part of the tissue, then that will be our cardiac output, right? So the cardiac output, right? And of course, the blood will flow through the artery, through the vasculature, to get to the, it's going to get to the tissue, right? And at the level of the tissue, once the tissue uptakes those oxygen, the oxygen will go to the cells are going to take up the oxygen, and the mitochondria, right, particularly the electron transport chain, is going to use those oxygen to make ATP, right? And we're talking about the cytochrome C oxidase, right? Who is going to be using the oxygen, and which is also called, can see some tests, they call it complex 4. So which is present in the electron transport chain, and that will be using the oxygen to be able to make ATP for the body, right? And then after that, those, so as we are taking up the oxygen from the blood, the remaining blood is going to be the deoxygenated blood, and those deoxygenated blood, they want to move back through the vein, right? And then from the vein, they go back to the right atrium, right ventricle, and then we can pump them out again into the lung for oxygenation and start all over again. So just quick recap. So from atmospheric pressure into the airway, which is partial pressure of oxygen in the inspired air, right? Into the alveolar, right? Partial pressure of oxygen in the alveolar, right? From there into the plasma, right? And then from plasma to the hemoglobin. From hemoglobin, right? From there we pump it out, right? Cardiac output. And then from there, it's going to go to the level of the tissue, and we're going to use it to make ATP. The blood becomes deoxygenated, and it comes back for oxygenation, right? So let's quickly go through this pathway, right? One thing I want to mention before we continue is that anything that affects the atmospheric pressure will affect everything downstream, right? So if the atmospheric pressure is decreased, the PiO2 will decrease, the P capital O2 will decrease, your partial pressure of oxygen will decrease, the hemoglobin saturation will decrease, and of course, hypoxia onto occur, right? Same thing, let's say the oxygen is getting to the alveolar, but it can't diffuse through, everything downstream will also be affected. So even though the partial pressure of oxygen in the alveolar is normal, but the partial pressure of oxygen in the capillary will be decreased, the hemoglobin saturation will be decreased, and of course that can lead to hypoxia. So let's quickly do some quick recap from our previous lecture. So how do we calculate our partial pressure of oxygen in the inspired air? So that would be our P barometric pressure minus water vapor pressure, right? And then multiplied by our FiO2. What about the alveolar gas equation? Anybody remember the alveolar gas equation, right? So alveolar gas equation will be our PiO2, right? Minus P water, right? Divided by respiration equation. So that will be our alveolar gas equation, right? And if you have not watched the video on the alveolar gas equation, I strongly recommend to watch that video. That will help you to understand the alveolar gas equation, right? And coming into the blood, right? So if you want to determine the oxygen in the blood, right? So to determine the oxygen in the blood, we use what they call the oxygen content. We're going to use oxygen content in the blood, right? And the oxygen contents in the blood, right, will be equal to the blood, because if you look at the blood, we have some oxygen in the plasma and we have some oxygen in the hemoglobin. So this is going to be equal to the oxygen that is bound to the hemoglobin. So oxygen bound to hemoglobin plus oxygen dissolved in plasma. And so the oxygen that is bound to hemoglobin is expressed in 1.34 multiplied by our hemoglobin multiplied by the oxygen saturation. Right? So this is going to be our oxygen bound to hemoglobin, right? And because for every one hemoglobin, is going to bind to 1.34 milliliter of oxygen. So that's how we come up with this formula. And we're going to add this to the oxygen dissolved in plasma, which is expressed as 0.03 multiplied by our PaO2, right? So this is going to be the oxygen content in the blood, right? So if we want to now calculate the oxygen delivery, so oxygen delivery to the tissue. So the oxygen delivery to the tissue, right? So looking at this diagram, we can see the two main things that will influence the oxygen that's been delivered to the tissue will be the oxygen content, right? And the cardiac output. So that means our oxygen delivery to the tissue will be equal to oxygen cardiac output multiplied by the oxygen content, right? And of course, cardiac output equals to stroke volume multiplied by heart rate, right? So stroke volume multiplied by heart rate. And then anything that decreases this oxygen delivery to the tissue, that's what is going to lead to hypoxia, right? So having said that, let's write out that formula so that we can apply it, right? So we can say that our oxygen delivery to the tissue is equal to cardiac output, right? So cardiac output multiplied by oxygen content. And oxygen content is 1.34 multiplied by hemoglobin multiplied by oxygen saturation plus 0.003 multiplied by PaO2. And that will be our oxygen delivery to the tissue. So anything that affects any of the parameter in this equation will lead to hypoxia. And in the next video, we're going to go through all the causes of hypoxia.